I would like to ask, in order, Brajesh, Joseph Saji, Liubov Kovalenko, Piotr Płonka, and Jossian Garcia. So please come here, align, and you have 2 minutes to present your results. So let me time it. Yes. So first is Brajesh, then it's like in the indico. Yeah, Brajesh, Joseph, Liubov, and Piotr. And let me put connect, then stop this one. Yeah, come over here. Come on, the first person. No. I have everything. It's full screen. Why? Okay, I'll have to move it. So go ahead. And so for the people in LIGO, they know it. There's like a lot of posters, and I can. There are a lot of posters, and usually the students, like people who are presenting poster, they have like 30 seconds. But here we are generous. You have 2 minutes. And then we take break. So yeah, go ahead.
Not the time.
Yeah.
So, good evening, everyone, and obviously, namaste. My name is Brajesh Kumar Padhi, and I'm from Trivandrum. I'm a summer student working under Dr. Marek Stapanchak, and I have been working this summer on the topic of supernova regions. So, I'll go through the basics once. As Mr. Murphy, Daniel Murphy, has already talked in the morning, uh, we have we can define a supernova on various regions, depending on the physical properties and the dominant processes in each of them. Uh, so yeah, I'll just go through these once, and so okay, so.
Here.
So yeah, so we have the core. So the core is, as Murphy told in the morning, the core is actually a spherical core, and we impose a spherical symmetry to some distance, and it's usually less than equal to somewhat around 8 kilometers. And then we usually go on to the regions, the 5 regions, region 1 to 5. But I will also define something called as region 0. So region 1 is the region dominated by the process of sustained ledu convection, and it is somewhat defined by the innermost and outermost layers are defined by having the mass convective flux of 5% of the peak value. So since the core is defined in kilometers, while you define the region 1 with respect to flux, you need to have something in between. So this something in between is usually the region 0. It's a buffer region. It is also nearly spherically symmetrical. So doesn't contribute much to GW signals. Yeah, so region 1. Then in region 2, it's usually the convective overshoot region. And the convective overshoot region is then preceded by the region 3, which is the PNS surface. Then we have the region 4, which usually has the neutrino net cooling layer. And the region 5 is everything else. So it is usually the shock wave up till the, I would say, from gain layer, the shock wave, and then the whole computational domain. So we define the supernova regions like this. Then I have been working on two progenitors primarily, D15 and D25, as Daniel Murphy and Coulter have already mentioned about it. So what we proceeded to do is we had the individual regional strain data for region 1 to 5. And since I'm a rookie, I started doing what rookies usually do. So I plotted the strains, the time series. And for the time series, I have actually not included the plot in here because it's not that necessary. But what we observed was region 1 and 2 usually had a similar time evolution with respect to their amplitudes, and region 3 and 4 had a similar different set of time evolution. You can, if you remember pretty well, Mr. Daniel also presented it pretty well, that in the beginning the strains are usually dominated by gravitational waves from region 3 and 4, and at the later stages it gets dominated by 1 and 2.
Okay,
So
that's right.
okay, okay. Okay. So what we do is we then club the regions. So R1, 2, you can see R1, 2 and R3, 4. And this plot is just to show that, yeah, what I'm speaking is not random things. It actually happens. So you can see in the beginning, R1, 2, and R3, 4 are comparable. So this is for 160 to 240 milliseconds. Previously, R3, 4 is more dominant. Then R3, 4 becomes less dominant, and R1, 2 dominates it completely. So we then proceed to do an envelope analysis. We take a 5-degree polynomial to envelope the different regions, and we just trace the whole time series and find the last point after which the amplitudes from 1 to exceeded that of 3, 4 and never returned.
Yeah, can we distinguish these regions?
Okay. So we define something as cross times, and then we plot it on
Hey, yeah. You have like 10 more seconds.
Okay, so we check it on spectrograms. Usually these are consistent. Then you would see across all different theta and phi values for a particular progenitor, these are consistent. But when you project them onto LIGO noise, these get the system doesn't remain consistent and robust, and you cannot essentially differentiate the regions just based on the time series data. But we are working on it.
Okay,
do better.
thank you.
Yeah. That was
So it was a little bit longer, but
yeah.
And the poster will be available tomorrow.
Yeah, so
Okay.
I'm really sorry for the posters. It would be available tomorrow.
Yeah.
Thank you.
Mm-hmm. Here we go. Is the next one, right? Yeah, okay. Yeah.
Yeah, hi. Good afternoon. I'm Joseph. I'm a PhD student at Center for Theoretical Physics, Polish Academy of Sciences. So today I will give a brief intro to our work, GRMHD simulation of black hole disk systems. We focus on heavy element nucleosynthesis. So as many of must know, rapid neutron capture process is one of the main process by which heaviest elements in the universe are produced. And from the event 170817, we know that binary neutron submergers are the robust sites. And coming to core collapse supernovae, not ordinary ones produce heaviest elements, but collapses and magnetorotational supernovae are found, like not observationally, I think, but there are many simulations which produce good amount of our process yields from collapses and rotational supernovae. Now, in this particular work, we use GRMHD simulations using our code developed in Center for Theoretical Physics, EOS, with the tablet dedication of state and the neutrino cooling, and we combine it with nuclear reaction network to produce the abundance profile. So this particular results is for a black hole torus system, but it's mostly for a post-merger situation. We have the density electron fraction, and we use these tracer particles to extract the data to input into the nuclear reaction network. And here we have the abundance profile. And as you can see, these are like results from 4 different 3D simulations, and the blocks are the solar R process, solar abundance. So we were able to exactly reproduce the solar R process elemental profile. And in a way, I have in the poster, you can see the poster, we have also discussed how we can use this code to prospects of studying our process from collapses and magnetorotational supernovae. So please visit the poster. Thank you.
Hello, everyone. My name is Liubov. I am a PhD student at Stockholm University. This poster is based on a diptych of 2 papers, which aim to explore how the particular circumstances of the explosion, how the particular properties of the explosion mechanism influence the multi-messenger signal. And so for this, we perform 3D flash simulations, non-full GR. We take a high compactness 39 solar mass progenitor. The first one we leave as is. We take it to core collapse, then evolve it for about a second, at which point it collapses into a black hole. The second model, we add rotation, and for the third one, rotation and magnetic field. Since we don't do full GR, we use quadrupole moment equations to extract the gravitational wave signal. We do that, we compare those. That's on the matter side. On the neutrino side, we use the neutrino asymmetry equations to extract the gravitational wave strain here as well. What we do find in those is that all of those models produce distinct signals in shapes and in amplitudes. What that means is that should we be so lucky as to detect a core collapse gravitational wave signal, we should be able to understand exactly how this signal came to be.
Thank you. Well.
So, hello, my name is Piotr. I would like to make a short introduction to my poster about the study where we investigate the effects of self-gravity in collapsars. This topic is directly related with long gamma ray burst. So we implemented to harm 2 features. The first one is to dynamical evolution of the mass and spin of the Kerr black hole. And then we create a framework for self-gravity. And then we performed 2 3-dimensional GRMHD simulation to directly compare effect of self-gravity in such systems. So in my poster, firstly, you can find a few words about our implementation of self-gravity. How does it work? Then the effects of self-gravity on jet properties in collapsars in both models. Then there is discussion about the Kerr black hole evolution, I mean evolution of the mass and spin. And then there is a short discussion about the effects of electromagnetic transient. And at the end of the poster, you can find also information about the density waves in the accretion disk around the newly formed black hole, because these density waves potentially could lead to the gravitational waves emission. So if you have any question or if you would like to know about the implementation of self-gravity, feel free to ask anytime. Thank you.
Thank you. And we don't have the last speaker for the poster sparkler, but maybe we can have a 10 minutes break and then we reconvene with the discussion. Just a few minutes. He's online. He wants to speak online. Ah, hey, Joseph.
Can you hear me? Sorry.
Okay. Yeah, go ahead.
Okay, thank you. Well, I'm presenting our work. Well, firstly, good evening. I'm presenting our work of using generative adversarial networks to generate gravitational wave signals from core lab supernovae. Well, firstly, I would like to say that we use the state-of-the-art architecture, which was developed by Donnet et al. And we also use the Richards et al. Catalog of gravitational wave signals. We classify this catalog into 5 classes to train our network. And to evaluate the results, we use 2 approaches. First, we use similarity metric, which in this case I present the match function, and also we analyze the distributions of the signals of the generation and the training to see how well the generator produces signals. And overall, the results show that our network is able to produce to generate signals with the same properties, general properties as the training set, and also maintaining the separability between the other classes, which is good. And well, finally, I would like to say that these are examples of generated signals. So we can see clearly that I think I didn't mention, but the conditional variable in this case was the beta value, which is related with the rotational energy at core bounds. So we can see a relation between the class, and the higher the class, also the higher the core bounds. So I think so. Thank you.
Thank you. Okay, that's everybody. So maybe we can take a few minutes.